Hi, everybody. Hi, everybody. Welcome back. I'm Rod, and it's Rod's office hours. We're going to do some oil industry insights. We had a good session last week on artificial lift. Um, I and please put your questions in the Q&A section. I missed a couple last week, but there were some really good questions in there, and we'll try and cover off some of those tonight. So on artificial lift, we spent quite some time on rod pumps, and then we still have a number of artificial lift types to discuss. But first, I thought I would. There was some questions over some of the rock mechanics and some of the IPR, the inflow performance relationship, the vertical lift profiles that we went through. So I'm going to spend a little bit of time on that tonight, just reviewing that. A little bit about myself. My name is Rod Gibbons. I am a petroleum engineer and entrepreneur in the oil industry. I've been working in the industry for about 30 years now, both onshore and offshore. Me and my wife work together in the industry. I've worked in the field and the office as an engineer, manager, consultant, business owner, and had the opportunity to work in a number of countries, including Canada, US, Australia, Southeast Asia, and Europe, different countries in Europe. So I want to focus on sort of the practicalities of working in the oil industry, and just share my experiences with you, which is the premise of this whole time, these videos. But to get back to artificial lift and IPR, something that I just wanted to refresh on was the concept of an oil reservoir or gas reservoir. And we think of it as a big pool of oil under the ground, but actually it's actually contained in reservoir rocks. So these are cores of sandstone. And so lots of times reservoir will be either sandstone or limestone. So sandstone is basically sand, like a beach or desert, that's over time gets compressed and solidified into sandstone. And limestone is like a reef that gets buried and deposited and turns into limestone. And so it's not a big cavern of oil. It's actually within the pore spaces between the rocks and potentially in the fractures as well, in the naturally occurring fractures in the rocks as well. So, and that brings me to two kind of concepts, which is porosity and permeability. So, here's a couple of definitions. So, porosity is the amount of empty space in a material. How porous is it? So, when you think of styrofoam, it's got a lot of air in it. It's porous. Permeability measures how easily fluids can flow through these spaces. So, a lot of styrofoam, it's light and it's got a lot of pore space, but they're not connected. So you don't get a lot of liquid flowing through a piece of styrofoam, for example. So if I were to use an example, if this glass with these ice cubes in it, if the ice cubes are actually grains of sand, then in your glass there's actually space. The glass is full of ice, So, and if you think in a reservoir that's buried underground, there's enough contact with the ice cubes that it supports the weight of the rock above it. So you can say it's full. But if we fill it with, pour some liquid into it, then it's actually filled up the space between the ice cubes. And how much space, how much liquid you can get in there, that's actually a measure of the porosity. So sometimes when you have a really fine shaven ice and you get a nice drink, you don't get much, you can't drink much out of it because it all gets bound in between the ice cubes are so close together that you don't get a lot of drink in there. So that's porosity. And permeability, again, is if you have different sizes of ice cube of rocks, then it's going to be easier to find a pathway through the rock. So that's porosity and permeability. Next time you have a drink, then you'll think of that. So graphically, if each one of these is, if we were to magnify it, and this is a sand grain in sandstone, then when the grains are tightly packed together, it's not porous, there's no porosity, and it's not permeable. Then you can have a case where it's porous, there's spaces in there, but they're not connected. So then it can't have flow, then it's non-permeable. And then porous and permeable, there's spaces and liquid can flow through it. And that's very important in oil and gas production, is because if you don't have this porosity, then the volume of gas or the volume of oil is not very big. And how it flows through the rock is a measure of how productive the well can be. And so this is we sum all this up in our inflow performance relationship from last week, which we'll cover here a couple slides down. So you may remember this schematic. If we kind of zoom out from the microscopic to sort of at the field level, you have your production well producing oil, and then water injectors that is supporting the field, support with pressure support. So as you get, as you say, open this well up, the pressure in the reservoir will drop because you're taking fluid out and the pressure goes down, like letting the air out of a balloon. It's not a balloon, it's rock, but it's like letting the air out of a balloon. You're taking the oil out of this area. Well, when the pressure gets low here, if the pressure's high here, all that fluid wants to go to that well, which you can see in this sort of cross section here. It wants to go towards the low pressure. If you were to look sort of, one of the issues with that, that's fine. Even when you have a very nice porous sandstone, one of the things that'll happen is if you have a 6-inch hole or a 7-inch hole drilled down into the reservoir, all that oil and gas is all trying to get into that small space. So even if I have lots of porosity out here, and this is the straw is the well that I poked down there, it has to kind of fight to get into the bottom of the well because this is the low pressure point. It's all flowing down here, and so you can kind of see that in a bathtub. When you pull the plug in the bathtub, all the water is trying to get out of one little pipe. It doesn't happen immediately. It takes time for that water to all fit down into that drain. That's similar to what's going to happen when you start taking oil out of a reservoir. All of that stuff has to flow into one point. It starts to choke each other off and compete with each other. Question here. Why does the water go to the pressure? It looks far away. Is the pressure that strong? Absolutely, it is, and it is if this is our pressure sink, so our drain in our bathtub, you can imagine that if in an ideal world where if the rock is all or the ice cubes in my glass, if they're all the same, so that they're homogeneous. So if they're all like this, then yeah, that when that pressure drops, that pressure wave, like when you throw a stone in a pond and that wave ripples out. When you draw down that pressure, that pressure wave goes out into the reservoir. It can go a long ways. If you have a interruption in your geology, so if you have a fault, so that or a fracture, or the rock type gets a little bit, we call it tight, where it's not as permeable, then that restricts that pressure pulse going out. And so a lot of times when you drill an exploration well or a delineation well or exploration well, say, you'll do a flow test and you actually will produce some of the oil out of the reservoir and measure the pressure downhole. And by measuring that pressure, you can estimate how big the reservoir is, how much porosity is in there, because you're basically sending a pressure pulse out into the reservoir. So there's quite an interesting field in petroleum engineering on well testing and interpreting well tests, so that you can see, and a lot of times you can even see the excuse me, where the faults are. So yeah, you can see a long ways out. Of course, the longer you can measure, the longer time you have to measure, or the more volume you take out, then the further you can see, because the further the pressure pulse travels in the reservoir. So that's one of the well testing is great to see the oil, coming over the rig tank, but actually there's quite a bit of analysis that goes along to estimate how big the reserves and resources. So again, a lot of geology, a lot of fluid dynamics. There's a lot of different equations to describe how the fluid flows through that sort of system. But as we talked about last week, all we're going to do is worry about our inflow performance relationship. So as say working engineers, production engineers, you want to know how my well is doing. So I have my initial reservoir pressure. When I drilled the well, I drilled into a pressure, hydrostatic pressure, or it could be slightly overpressure, but I got a pressure reading. That's my reservoir pressure. Then, and this graph just plots the pressure, the flowing pressure in the well at the bottom of the well, say right here, against the flow rate. So, and if you think about it on surface, you see those valves, those wing valves. Okay, I'm going to open the valve. As I open the valve, I'm dropping so what it does is it lets some liquid out of the well. So there's less liquid in here, so the pressure goes down. Like when I let some air out of my car tire, I open the valve and some air goes out, the pressure drops. Now, unlike my car tire, which is a closed system, I'm connected to a bunch of rock, and there's a bunch of pressure in that rock. And so it starts to flow towards the well. So, but again, it gets choked off as it's going towards the well. It's coming, say, from a kilometer away, and it's coming all in, and it's only trying to get through a 15-centimeter hole. It takes time to do that. Plus, depending on the rock properties, how fast it can move through the rock is also a question. If there's fractures, it can go a lot faster than if it's just, say, the matrix porosity. So I can probably open that valve faster than the reservoir can fill the wellbore back up with fluid. So my pressure drops. So I open the valve and I drop the pressure. Dropping the pressure at the surface, that drops the pressure here at the sand face in the wellbore, and then the well flows at a certain rate because of that. So you can think of, if I have a garden hose and I'm opening the valve on the garden hose, the water's flowing out. What I'm doing is I'm dropping the pressure at the end of the hose, and the water just keeps coming. So at a certain flow rate. So if I know what it is when it's zero, when it's shut in, what the reservoir pressure is, and I open the valve a little bit and I drop the pressure, I get a new flow rate. Well, if I have a straw, the flow rate I have is pretty low. A garden hose is bigger. A fire hose would be a lot more. So the initial thing you're looking for is, how big a well is this? How productive can it be? And that is how good are the rock properties? By doing this simple flow test without any sort of complex math, all I'm doing is, I dropped the pressure, I got this flow rate. So I know, hey, if I drop it more, I should be able to get this flow rate. And it's pretty well a straight line. There's a little bend here at the end. Because oil, when the pressure drops, bubbles come out of solution. It changes. It doesn't flow as good when you're going at lower pressures. But for the most part, it's a straight line. It tells me if I open the valve this much, if I open it half, I get this much rate. Open it full, I get more. So this tells you a lot about your reservoir properties and your wellbore properties. One of the things that can happen is formation damage. So, and we call that skin on the reservoir. So if you think about from the inside of the well, I have a scum layer or a skin of damage on the inside of that wellbore. That's going to restrict my flow even more. So over here, this is drawn. This is the wellbore, and this is the perforations, and here's the perforations in the injection well, and it's flowing along here. And you see, this is all nice and open. There's no, so I have my natural restriction that's happening because I'm all this pressure is going into one center point. But right at that wellbore, let's go back. If my reservoir looks like this, and so I've got a really nice reservoir, but right where I drilled my well, I crushed a bunch of that rock, or I put a bunch of chemicals or solids right next to my wellbore, then I'm getting a good pressure response, but my rate is a lot lower than it should be. This is formation. This could be formation damage right next to the wellbore, and a lot of times what you'll see, a telltale sign of that is when you open the valve, the pressure drops very quickly, and when you close the valve, the pressure comes up very quickly. It's going across a very it's not coming from way back here in the reservoir building up. It's very close to the wellbore. The pressure's still really high here. It's got to get across this damage. It builds up really fast. So that gives you a sign that you might have formation damage. And so, but we can draw that graphically. Again, if this first line is like a fire hose of oil and gas, but then a week later, it's now we shut in. We're still at the same reservoir pressure, but when we open it up, it doesn't flow very well at all. It's like a garden hose. Then chances are there could be some damage to the wellbore, which is referred to as skin. So that's one of the things that inflow performance relationship can help us diagnose. And it's very simple. We just got to collect two pieces of data. How much pressure are we flowing at, and what's our flow rate? And so that can tell us a lot about what's happening near wellbore. So and this is our inflow performance relationship, our IPR curve. So that tells us, so all of those rock properties, all that formation damage, all the geologic complexities, we can just summarize it with one straight line from a production point of view. The next thing we talked about, which I'd like to cover again, was vertical lift profiles. And so now that I'll just go back again. Sorry about that. Now that so our IPR inflow performance relationship, now we've got our droplet of oil into our wellbore. And we can learn a lot about the geology and the reservoir rock from that behavior, and from the near wellbore damage or how good that is. Now we've got our molecule of gas or oil inside our well that we drilled. So great, that's great. The issue now becomes with all oil and gas wells, one of the big things now is they're very deep in the ground. You can have oil wells at 500 meters or 500 feet, and you can have them down to over 3,000 meters or 10,000 feet. But we're always concerned with this up and down issue, getting the oil from the bottom of the well to the top of the well. And that's the vertical lift profile. So what makes that hard? Well, hydrostatic pressure. And this is a concept of when you're swimming or diving and you go down in the water and you go down 10 meters, you can feel it on your ears, that pressure. What you feel, that pressure that you feel, that is actually the weight of the water that's above your head. That fluid column is acting on your ears. It's on your body, but you really feel it in your ears usually. And what's also kind of interesting is It doesn't matter if you're 10 meters deep in the ocean or you're 10 meters deep in a swimming pool, the pressure is the same. It doesn't matter how big the pool is, it's how high above you that water is. That's what gives you that pressure. So, and it's a very important formula or concept in the oil industry, because again, this is getting the oil from the bottom of the well to the top of the well. So if we think about our scuba diver down at the bottom of the well, there's a lot of pressure on that diver. As he comes up to the surface, it's going to get a lot less pressure. So what's the formula for that? Well, pressure equals density of the liquid, of the fluid, times gravity times the height. So if we look at, so you have the density of, so because we want to know what that reservoir pressure is, we want to know what that bottom hole pressure, we want to know if we're diving, we want to know how deep we can go, because how much pressure is going to be acting on us. Well, so density is the first term. This is a bucket of water here, and this is a bucket of cement. A bucket of water is pretty heavy. You know, it's a kilogram for a liter. But a bucket of cement is a lot heavier because it's a lot more dense. So the density is really, the molecules are packed together more. So if you think of air is not very dense at all. It's not very heavy. Water, okay, that density goes up. Cement, you're getting water and solids in there. That's a very dense, probably could be up to 1.6 times as dense as water. Same sort of thing when if you take flour and add it to water, the density goes way up. That gets a lot heavier because it's solid, and so there's a lot more stuff for a given say liter of liquid. So and in oil and gas, and oil is less dense than water. So if like the specific gravity of oil is probably 0.8 of that of water. So oil is always on top of water because it's lighter, it's less dense, and water is always deeper because of the density. But that's the first thing. In hydrostatic pressure, the density of the fluid matters. So same as if you're diving, the density of the fluid above you would matter a lot. The next one is gravity. The next term is gravity. That's just gravitational force. So, you know, and on the moon, it's a lot less than it is on Earth. But this is the thing that makes apples fall to the ground. This is what keeps us connected to the Earth. And this is what has the Earth going around the sun. On the Earth, the force of gravity, or acceleration to the gravity, is constant. So this because all of our oil wells are on Earth, we use the same gravitational force. So we have to add it in. It's 9.8 meters per square second, but it's like that everywhere. There's some small variations, but for the most part, because what it's doing is it's taking that dense fluid and it is drawing it down towards the center of mass of the Earth. So it's always in the down direction. And I say down, like in the yeah. It's always, gravity doesn't change its direction. It's always acting down. Apples always fall down. But it's an important term in calculating your hydrostatic pressure. If we were drilling for oil and gas on the moon, our density, our gravity would be less. And the last term is height. And this is, so we can't adjust gravity. The density of a fluid we can change. And so you might hear the term drilling mud. We're actually taking water and we're putting additives in there to change its density, to change its properties. And it's referred to as mud, but it's actually a chemical combination of materials. So we can adjust density and height. So hydrostatic pressure depends on height. If you're a diver and you're at 10 meters in the ocean, you won't feel as much pressure as if you were to go to 100 meters on your ears. There'd be a big difference. And what you're changing is the height of the fluid above you. So you can see in this example, the height of the fluid above the straw here is less than it is here. So do my demonstration. So here, when the straw is at the bottom, I have to blow, not too hard, but a little bit hard. I'll bring it up halfway. Super easy. So I don't need to blow as hard to make bubbles shallow. When it's deep, I've got to blow harder. I need more pressure because the height of this water is pushing back on my breath, on my bubbles. So that's hydrostatic pressure. And so it's density of the fluid, acceleration due to gravity, and the height. So that really, using that formula, we can draw this vertical lift profile curve. So, and what this is if I take my pressure at the bottom of the well and I start to drop it, dropping that pressure, my flow rate is going to increase. Going this way, flow rate's increasing. So if I'm blowing more bubbles, things are rising faster. I'm reducing the density when I'm putting bubbles in there. Now, you would think this curve kind of should go a bit straight, like straight down. As I reduce the density, as I reduce my pressure, you would expect my flow rate to go faster. This does have a curve in it because just a weirdness of liquids. As I'm flowing up that pipe faster, I actually get frictional force. There's more friction. So that's why a bigger garden hose, you can get more water out of it for the same pressure than a smaller one, because that smaller hose is choking back the flow a bit. So you get this bit of a bend in this curve. But that's the physical thing that's happening, is we're looking at the hydrostatic pressure here to get from the bottom of the well to the top of the well. So, and you may recall from last week, so this is the green line is our inflow performance. So how if I'm an oil molecule, how do I get through the rock and get into the well? And then this brown line is, okay, I'm an oil molecule. How do I get from the bottom of the well to the top of the well? Where they intersect, I know what pressure I'm going to flow at. I can say what my flow rate is going to be, how fast I'm going to go. Because one of these is going to control me. It's either getting through the rock to the well or getting from the well to surface. And so if we're here, everything's going good. The well just continues to flow. Life's good. Oil comes into the well. Oil goes up the well. Where we get into issues is where there's no solution, where these lines don't cross. So now this is how the oil getting into the well, but this is the oil coming out from the bottom of the well to the top. So I might be able to flow into the well, but I can't get out. So then you have what you call a dead well. The well stops flowing. So, and there's quite a few causes for this. A lot of in the initial phases, again, in the more olden times, people would open the valve, the oil would go over the drilling derrick, and they just produce the oil. Well, what would happen would be the reservoir pressure would drop. And as the reservoir pressure dropped, then now this inflow performance relationship, there's not enough. When I get my oil molecule from the reservoir into the wellbore, there's not enough pressure left there to get up to surface. So then there's no intersection here. Another thing that could happen is if I'm producing my well and I've started water flood to keep the pressure up, because I don't want to get here. I keep my reservoir pressure up, but now I've started to make water at the producer. Well, the thing about water is it's denser than oil, so it's heavier. So it's a lot harder for it needs a lot more pressure to get from the bottom of the well to the top of the well because the density is higher. So again, this makes another situation where you have a dead well. And having a dead well is not the end of the world. It's actually, I would say, it's more common scenario. Normally, a naturally flowing well is only in early life of a field. Almost all wells would be dead wells for natural flow. And I say dead wells, just need to be a little bit careful on that because there's two things when we talk about dead wells. One is a dead well, it won't flow into a production system. So into a flow line, into a gas plant or an oil battery where it can be separated, where the oil, gas, and water can be separated. There's a certain pressure it needs to get into that system. There's another reference to dead well in a drilling or well control situation where will it flow to atmospheric pressure? So if the Christmas tree gets knocked off or there's some sort of situation, so you can have a dead well that won't flow to a production system, but it could still potentially flow to atmosphere. So you still have to treat it as a live well, just from a well control point of view. So, but from a production standpoint, if a well will no longer flow naturally, then you need to give it some extra energy to get it to flow to surface. We can do water injection. That gives extra energy into the reservoir. The next thing we can do is artificial lift in the wellbore itself. And so you can put a rod pump in the well, electric submersible pump, progressive cavity pump, plunger lift, gas lift. And we did have a question from last week, what's the most common types? Rod pumps by far are probably the most common. Again, a very high efficiency system, and lots of the moving parts are at surface, so that's a lot easier to deal with. Electric submersible pumps also very popular. Again, a rod pump can only lift a certain volume of fluid based on the pump diameter and how long of a stroke. And so there gets to be where pump jacks get so large, it's not really practical. So whereas an electric submersible pump, the pump and motor is in the well, and so it can do a lot higher volume rates. So more high volume wells, electric submersible pumps are quite popular. Progressive cavity pumps, probably less so. That they are good for pumping solids. So they've got a very specific use case. Plunger lift also, I would say, pretty popular in some onshore applications, because you're actually moving a metal plunger up the well, and so that works good. Onshore, offshore is not so good. Offshore gas lift is very, very popular option. And I guess the reason for gas and gas lift, which we'll talk about later, you're actually just putting gas, compressing gas and putting it into the well and bubbling it into the fluid, which has the effect of making it a lighter density. That way it can flow from the bottom of the well to surface easier, because the density is less. And that's probably the most popular offshore. And it's popular offshore because you have a lot of gas compression offshore for fuel gas. And so it's a natural thing to just be able to use that same dried gas that's there at the location and just put it back down to help lift the wells. So yeah, so rod pump gas lift is very popular, and so is ESPs. That's probably the most popular types. And we did talk about rod pumps last week. Again, 2 valves, ball on a seat. One travels up and down, the other stays in place. Again, this is providing the energy to get our oil from the bottom of the well to the top of the well, and reduces the pressure down at the bottom of the well with each stroke. So, and then we still have artificial lifts to cover. Next session we'll talk about electric submersible pumps, but I thought it was important just to go back through and have a discussion over how inflow performance relationship and vertical lift profile, specifically around hydrostatic pressure. Those are 2 important concepts that it's good to have, because then no matter what sort of artificial lift system we're using it for the same reasons all the time. Again, adding energy into that wellbore to get the fluid to surface. So just see if there's any further questions. No, I think that's it. If you have any questions, please feel free to send me an email. I'll just go through. This is for next week. But yeah, next week, Wednesday, 9 o'clock, Newfoundland time, 5:30 in Alberta. See you then, where we'll cover some more artificial lift and other concepts from the oil and gas industry. Okay, thanks. Bye.